K. Paranivelu, Professor at the Center for Environmental Studies and Director of Center for Climate Change and Disaster Management, Anna University, Chennai. He obtained his PhD degree from Indian Institute of Technology, Madras, Chennai. He worked as project officer for a brief period at IIT Madras and moved on to the Center for Environmental Studies, Anna University in 1992. He was a visiting professor at Chungam National University, South Korea during 2007. He has been teaching courses on environmental chemistry, environmental pollution control, and instrumental methods of analysis since last 27 years. He has guided 75 students for ME and MSc, 4 MPhil, 2 MS, and 15 PhDs. He has published 135 papers in journals and 90 in conference and symposiums. He has received several awards in national and international levels.
Welcome to the lecture series on chemistry of the environment. We are discussing about fundamentals of chemistry relevant to environmental studies. So far we discussed about stoichiometry, thermodynamics, kinetics, chemical equilibrium, and nuclear chemistry. And today in this line we are going to discuss about another fundamental things which will be relevant to environmental field is electrochemistry. In this electrochemistry, that is, the name itself indicate electrons. What are the electrons play around with the chemistry for the environmentally relevant things we are going to discuss in this electrochemistry. So, the name itself, as I told you, involves the study of chemical processes that actually cause electrons to move, and this require two electrodes, anode and cathode. For this, that is, in the cathode, reduction of materials will take place in this electrode, whereas in the anode, oxidation of whatever the pollutants will take place at this. So, during this process, reduction or oxidation, electrons will move across the electrode through this current, and that will be noticed. So, the movement of electrons is usually noticed by the electricity, which can be generated by movement of electrons from one element to another element in a particular chemical reaction, and this is actually known as oxidation reduction or popularly redox reaction. So, any chemical species which undergo oxidation and reduction, that is, it should take place simultaneously. Only one alone may not take place alone. Both oxidation and reduction should take place simultaneously, because of through this movement of electron is taking place. And these reactions usually known as redox reaction, and that involve a change in oxidation state of one or other elements. There will be a change in the oxidation state of the particular element will take place. And when a substance loses an electron, normally it is said to be oxidized. That is, its oxidation state increases when it loses electron, and because of this it is oxidized. Whereas, when a substance gains one electron, its oxidation state is usually decreases, and because of this it is being reduced, and this is what known as redox reaction. For example, we will consider this reaction. Hydrogen loses one electron and becomes H plus. So, hydrogen molecule loses 2 electron and forms 2 H plus ion. This is actually known as oxidation reaction. And reduction reaction, for example, chlorine molecule can pick up 2 electrons and gets converted into 2 moles of chloride ion. And if you see the overall reaction, hydrogen gas react with the chlorine gas, forms hydrochloric acid, and this is actually a redox reaction. Hydrogen reacts with the chlorine, form hydrochloric acid, is actually involves redox reaction, in which movement of electrons from hydrogen to chlorine is taking place, and chlorine accepts electron and gets converted to chloride ion. So, there are 2 types of electrochemical cell. One is called voltaic or galvanic cell, the other one is electrolytic cell. These galvanic cells are electrochemical cells actually that contain a spontaneous reaction taking place in this anode and cathode, and always have a positive voltage arising out of this galvanic cell. And during this, what has happened is the electrical energy released during the reaction can be used to do work. And a voltaic cell consists of two compartments called, each one is called half cells. The half cell where oxidation occurs is usually in anode. The other half cell where reduction occurs is a cathode. The electrons in voltaic cell flow from the negative electrode to the positive electrode, that is from anode to cathode, the flow of electron will take place. And electrodes are the sites of the oxidation and reduction reactions. Actually, it takes place, that is a redox cathode and anode oxidation. So, always the cathode reduction will take place and in anode oxidation will take place in the voltaic cell. And usually the two half cells, normally we write it with a cell diagram, and this is one half, the other one is half. Consider the Daniell cell, in which it consisting of zinc electrode and zinc sulphate solution. Similarly, copper electrode with a copper ion solution. And in this, zinc is continuously oxidized and producing aqueous solution of zinc 2 plus. That is the anode. Zinc will continuously undergo oxidation, producing electrons and zinc 2 plus ion. And conversely, in the cathode, what happens is copper ion present and it is in copper wire contact, the copper is reduced and continuously deposited onto the copper bar, that acts as actually the cathode. So, copper 2 plus will pick up 2 electron, get reduced to copper metal. So, as a result, the solution containing zinc becomes more positively charged, as a solution containing copper becomes more negatively charged, because copper 2 plus ion is removed and converted into copper metal. So, positive charges are decreasing, and this is what the cell diagram. If we consider the cell potential, that is actually the cathode minus anode, that is for the copper it is plus 0.347 volt, and whereas for zinc it is actually the minus 0.763. So, if you put this, the overall electrode potential comes positive, that is plus 1.103 volt is a voltage or electrode potential arising out of this Daniell cell. This can be converted into energy, and the cell potential is very important, that is different for each voltaic cell. The Daniell cell we have seen it is 1.1 volt positive, and its values depend upon the concentration of specific reactants and product as well as temperature of the reaction. Usually the standard cell potential we take it as a 25 degrees Celsius as a temperature for electrochemical reaction as a standard, and suppose the concentration of the reactants and products, if we keep it at 1 molar and the reaction occurs at 1 atmospheric pressure, the standard cell potential usually denoted by E naught and can be written as oxidation potential plus reduction potential, that is for voltaic cell it is equivalent to cathode standard electrode potential minus anode standard electrode potential. That difference comes as a total voltaic cell. As we have seen before, if it is positive we will get energy out of it. Consider another redox reaction in which at a standard condition in which the oxidation of vanadium 2 plus by ferric ion. Here ferric getting reduced to ferrous and vanadium 2 plus getting oxidized to vanadium 3 plus. At a standard condition, the E naught value for a conversion of ferric to ferrous is 0.77 volt, whereas for the oxidation of vanadium 2 plus to vanadium 3 plus the potential is minus 0.255 volts. So, if we put this for this cell, particular cell forming a galvanic cell, the potential becomes 1.026 volts. So, this potential difference is called cell potential, also known as electromotive force EMF value, and this value is positive, definitely this reaction is spontaneous. And for a spontaneous reaction, E cell should be positive. That means the free energy, the thermodynamic parameter, this already we discussed. The relationship between the free energy and the cell potential is equivalent to delta G is equivalent to minus N F E. E is the electromotive force cell. If it is positive, definitely the free energy will decrease. This is what the relationship between thermodynamic parameter and the electrochemistry. So, based on this potential, we can easily say a particular reaction is spontaneous or not, and the voltaic cell will function or not, produce a energy out of it. Generally, free energy decrease is a spontaneous process, whereas here the electromotive force is positive, definitely that particular redox reaction is positive or spontaneous. And already we discussed this relationship also with the equilibrium constant when we discussed about equilibrium value, and delta G is equivalent to minus R T ln K. K is the equilibrium constant value. The value is large enough, then again the reaction is feasible and spontaneous. This is what we discussed, the thermodynamic and equilibrium parameters, whereas here it is a thermodynamic and electrochemistry relationship about predicting about feasibility or spontaneity of their particular reaction. And these are all again can be very usefully explained based on the Nernst equation, that is the potential developed by a concentration cell using the Nernst equation can be explained. The potential developed by the concentration, that is a galvanic cell. And the Nernst equation is derived from the Gibbs free energy again at a standard condition, redox and oxidation, and this is related to free energy delta G is equal to minus NFE. That is a general condition at a standard one. So, the Nernst equation can be a lot of steps involved. I am giving the ultimate equation, standard potential minus R T ln divided by N of ln Q is equivalent to the electrochemical EMF force cell, and this is also sometimes N is a number of electron and also sometimes represented by Z, and that depends on oxidation and reduction species of this reaction, that is called quotient. And so, this potential is equivalent to standard electrode potential minus 2.303 R T divided by N of into log 10 Q. The ln it is converted by multiplying by 2.303 into, that is converted into log, and at a standard temperature 25 degrees Celsius, and putting the value of R and F, Faraday's constant, everything, and this term reduces to 0.0592 volts, and ultimately this potential equation, that is cell potential is equivalent to standard electrode potential minus 0.0592 volt divided by N, that is the number of electrons involved, but it may be 1, 2 or 3 electron transfer, and log 10 Q, that is a quotient. So, ultimately what the information we get is when the K value is greater than 1, also the standard EFM value is greater than 0, then the reaction powers product formation, that is the reaction is spontaneous. And suppose the equilibrium constant value K is less than or closer to 1 and E naught value is a negative value, then the reaction powers a reactance formation. That means the reactance is not feasible, not spontaneous. And the electrochemical, another cell is electrolytic cell. We have discussed about galvanic cell. The other one is electrolytic cell. This is also important. And here the electrolytic cell converts electrical energy into chemical energy, or reverse of this. That means, in this cell the redox reaction is not spontaneous, whereas in the galvanic cell based on the cell potential it is plus, it is definitely possible. Whereas here what we have to do is we have to provide or supply electrical energy to drive out or initiate the reaction. Externally we have to provide electrical energy to the cell consisting of electrolytes with the anode and cathode. To run it, we have to supply energy. On supplying current, the ions consisting of both positive ions and negative ions move towards the appropriate electrodes, that is with opposite polarity, and simultaneous reduction and oxidation will take place at the appropriate electrodes, that is anode oxidation, cathode reduction will take place. For example, consider the electrolysis of solid sodium chloride in the ionic form. Okay, at a very high temperature, let us assume this reaction is taking place, and if we pass current through this cell of a sodium chloride electrolyte, what happens is sodium ion will move to this cathode and pick up electron, get reduced to sodium in the molten state. Simultaneously, the chloride anions will migrate towards the anode, where it loses one electron and gets oxidized to chlorine gas, that is chlorine will be liberated here. So, the overall reaction is deposition of sodium ion and chlorine. So, this is a reaction takes place in a high temperature solid, and this is also possible in solution, aqueous solution, in which the ions dissolved can move appropriate electrode, again gets discharged accordingly. Another important law related to the electrolysis of this electrolytic reaction is based on the Faraday's law. Faraday contributed a lot of things in the electric field, and there are Faraday's first law, second law. Faraday's first law is very, very important. That is the relationship between the quantity of electric charge passed through the electrolyte and the amount of substance deposit at an electrode is normally governed by the Faraday's law. And the Faraday's first law of electrolysis, that is when electric current is passed through the electrolyte like sodium chloride or other thing, and amount of substance deposited is proportional to the quantity of electric charge passed through the electrolytes. Let us assume if W is the mass of the substance deposited on the electrode by passing q coulombs of charge, and as per the Faraday's law of electrolysis, that is the weight deposited is proportional to the coulombs passed. That is q is nothing but I current into time, what amperes of current for what time of period. If we multiply, we will get a number of coulombs passed through the solution. So, W is proportional to I current passed as well as time, directly it is related, and the proportionality can be removed by introducing a constant Z, and this is a equation will take this form. Here the constant is known as electrochemical equivalent, and it is characterized by a particular chemical substance getting discharged at the electrode. So, the Faraday's constant F value, and it is a charge possessed by 1 mole of electrons, and if it is equivalent to 96,500 coulombs, that is a Faraday's constant value approximately. In terms of Faraday's constant, the number of gram equivalent of the electrolyte discharge at the electrode is equivalent to the Faraday's actually it is passed. That means, with this one we can get what is the amount of weight deposited at electrode is equivalent to equivalent weight of the particular substance into the number of coulombs passed, that is I into T, divided by the Faraday's constant value, that is 96,500. Using this relationship, we can find what is the amount of substance deposited at the cathode using this Faraday's first law of electrolysis. This is very, very important in this. This electrochemistry is also useful in environmental analysis purposes. For example, we can measure the electrical conductivity based on Ohm's law, and that is very, very important. We can quickly measure what are the salt content, TDS content, because electrical conductivity is related to total dissolved solid. Suppose we go for TDS measurement by gravimetric, evaporation, cooling, weighing, all these things, at least 4 hours it will take. but with the electrical conductivity within a minute we can get what are the electrical conductivity as well as the TDS. So, this is one of the very important application of electrical conductivity based on Ohm's law. Similarly, ion selective electrodes based on this electrical property measurement is again very useful. For example, determination of fluoride present in drinking water and pH value, all based on ion selective electrode. Similarly, we have other type of instruments used for polarography, especially anodic stripping voltammetry, especially for lead and cadmium, very useful, and thus usually again the deposition principle. First, cathodically reduce the metals like lead or cadmium on the cathode, and then anodically strip out and measure the current flowing through this at the anodic stripping voltammetric time. That is very popular for analyzing heavy metals like lead and cadmium. Also, we can go for coulombsmetry, number of coulombs passed through the solution, as well as we have coulometric titration to find out the environmental contaminant, and this using this electroanalysis technique. And the pH meter is a well known in all laboratory. We use this pH meter made up of a glass electrode, and earlier one we have two electrodes, one is a glass electrode and the other one is reference electrode calomel, and nowadays everything is combined. Even packet type of meters are available, in which very handy with the advancement in instrumentation. The pH meter, packet type of pH meter with a very low cost instruments are available, is again based on this electroanalysis. And similarly, as I mentioned before, conductivity, okay, DO, dissolved oxygen, and pH, everything can be measured instantaneously based on electrical things, multiple probe in which we can get pH and conductivity, DO, dissolved oxygen, again based on electrical sensor. One can be used for field level monitoring, that is on spot measurement. Another important electrochemical application is in treatment of water, wastewater, etc., okay, including soil remediation. These electrochemical techniques are very useful. For example, we have variety of techniques based on electrochemical driven things, especially electrolytic cell based one. Electrode deposition of metals, heavy metals can be deposited on the cathode using this electrode deposition principle. Electrocoagulation, we will see, I will explain what is this. Similarly, electroflotation, electrooxidation, electrodisinfection, electroreduction, and including electrodialysis with the membrane based one to remove the salt content, TDS and all, very useful based on the electrochemical treatment method. And the advantage with this is the electron is a reagent. All these things, electron, no other chemical additives that make this electrochemical treatment also very attractive. Plus, it possesses very high efficiency, easy to operate, and the facilities are very compact one, very small designed one. What we required is 2 electrodes and a power supply is sufficient to drive this electrochemical treatment. And the basic requirement of electrode is very important again. The electrode selector should have good activity, and it should come for long time with a high stability, and also it should be low cost. So, this is a requirement to drive this thing, because the electrode is a one, whether it is oxidation or reduction actually takes place. And some of the low cost electrodes are graphite and dimensionally stable anode with based on titanium and other combination, in which they can be used as a anode, because one of the nuisance with this electrode, anode usually will undergo dissolution and the activity also may be last during the course. So, that is important. Dimensionally stable anode material will come for long time without undergoing dissolution. Electrode disinfection is very, very important nowadays. Generating chlorine through passing current is a basis of this one. If you have chloride and if you pass current, definitely electrons will be lost and its chlorine will be formed at the anode. This is a reaction actually taking place, and this chlorine is a proved disinfectant. It can be used. Okay. Even at home we can make home disinfection using this. Take water, add salt and a power supply, usually driven by solar is very, very handy to minimize the operating cost, and we can generate chlorine and use it for disinfection, floor cleaning, etc. is possible using this very simple technology. Simultaneously during this process, cathode reaction also take place. Water will pick up this released electron and gets hydrogen may be generated at the cathode, and hydroxide ion also be formed. Similar to chloride, we can generate a hydroxyl radical also. This is a much more powerful oxidizing agent than or disinfectant than chlorine, and this radical also can be generated electrically, similar to electrooxidation, especially with the electrodes like boron diamond doped electrode. Boron doped to the diamond is one proved to generate hydroxyl radical that will be very powerful oxidizing agent. Other electrochemical methods are electrocoagulation as well as electrodeposition is possible. Electrocoagulation for water purification, wastewater treatment, etc., it is very, very useful. Okay. That is, we have to generate coagulant by passing current, and anode selection is very important here. And for example, if you select aluminum or iron electrode, make it as an anode, what happens is if you pass current, the anode material will undergo dissolution. Aluminum metal or iron metal will go into the solution generating aluminum 3 ion. This aluminum 3 ion will undergo hydrolysis immediately at the prevailing condition and form aluminum hydroxide or ferric hydroxide coagulant things, and all the impurities present in water or wastewater are getting removed here. So, this is a instantaneous generation of reagent, namely aluminum 3 or Fe3. Contrary to this, as electrode deposition is also possible for heavy metals recovery, especially from electroplating industry, there are residue of metal ions present, and through deposition at a cathode we can recover metal like nickel or whatever other things also is possible using this. Electrocoagulation can be floated also with some addition of surfactant may help you, instead of settling as a coagulant, that can be floated and bring it to the top, and electroflotation is another technique. So, to sum up, electrochemistry is also very, very important for environmental studies, in which electron is a reagent. The electricity is nothing but electron that is used to bring reaction, especially the redox reaction, very, very important. As we discussed, we have two type of cell. One is galvanic cell, in which it is a spontaneous one to generate or provide energy. The other one is electrolytic cell. It is a reverse of this. We have to supply electricity to drive out, to take the reactions, especially for environmental remediation. Analysis of pollutants is also possible based on electrical properties like current, voltage and conductivity. These are all the important things, current related properties that can be exploited for analysis of pollutants, because the pollutants may undergo redox reaction or change in potential or conductivity value will be changed. Accordingly, we can analysis of pollutants, as I mentioned before, pH meter, fluoride meter, these are all very important ion selective electrode. We can quickly measure electrical conductivity as well as other anodic stripping voltammetry, coulometry, other type of pollutants also we can measure based on this electroanalytical technique. And again, the electrochemical treatment methods are very important, and any pollutants, if they have charge positive or negative, are capable of undergoing redox reaction, then the method of electrochemical treatment is a method of choice, and which electron is a clean reagent to drive this reaction. We can go for water treatment, wastewater treatment to reduce toxic metal, to reduce the amount of dissolved impurities, as well as even electrokinetic remediation of soil, again very important, in which the pollutants present in the soil are through process of electroosmosis and electromigration, they can be removed and contamination can be remediated through electrokinetic remediation of soil, also very important. So, with this we have come to the end of this session on electricity or electrochemical methods for treatment of environmental studies, including analysis and treatment. Thank you.